what is meant by the term enthalpy of the reaction. Let's try to understand. My dear students, enthalpy of the reaction, it is defined as the amount of heat absorbed or released. The amount of heat absorbed or released during a chemical reaction. During a chemical reaction. The amount of heat absorbed or released during a chemical reaction, carried out at constant pressure. Carried out at constant pressure. Carried out at constant pressure. What it means exactly? Let's have a look. For example, I am taking a general reaction over here in which reactants are getting converted into products. This is a general reaction in which reactants are getting converted into products. Okay, this one general reaction. My dear students, I am assuming that this particular reaction, it is carried out at constant pressure. I'm assuming that this particular reaction in which reactants are getting converted into products, I'm assuming that this particular reaction is carried out at constant pressure. Now, my dear students, when this particular reaction will be carried out at constant pressure, definitely there will be some amount of heat absorbed or released during the reaction. Absolutely. My dear students, that amount of heat which is either absorbed or released during this particular reaction, that amount of heat which is either absorbed or released during this particular reaction, which I'm representing with QP, amount of heat absorbed or released during this particular reaction, which is carried out at constant pressure. The amount of heat absorbed or released during this particular reaction, which is carried out at constant pressure, that is something which I call as enthalpy of the reaction. So first of all, what is enthalpy of the reaction? How do you define the term enthalpy of the reaction? Let me quickly tell you. It is the amount of heat which is absorbed or released during a chemical reaction which is carried out at constant pressure. Right? I believe this is clear to everyone. Okay? So my dear students, from now onwards, how exactly you are going to define the enthalpy of reaction? Either you call it enthalpy of the reaction, or you can call it as enthalpy change in the reaction. The choice is all yours. Either you call it as enthalpy of the reaction, or you can call it as enthalpy change in the reaction. What is meant by it? The amount of heat which is absorbed or released during a chemical reaction which is carried out at constant pressure. Point number one. Point number two. My dear students, imagine the same reaction. Imagine the same reaction was being carried out at constant volume. Imagine the same reaction was being carried out at constant volume. At constant volume, whatever amount of heat will be absorbed or released during the reaction. At constant volume, whatever amount of heat will be absorbed or released during the reaction. That is something which you call as internal energy of the reaction, or you can call it as internal energy change in the reaction. So there are two terms which I have defined. One is enthalpy of the reaction. One is internal energy of the reaction, or you can call it as enthalpy change in the reaction, internal energy change in the reaction. Let me define both the things again. Enthalpy of the reaction or the enthalpy change in the reaction. It is basically the amount of heat which is absorbed or released during a reaction which is carried out at constant pressure. Internal energy change in the reaction is the amount of heat which is absorbed or released during a chemical reaction which is carried out at constant volume. Right? Which is carried out at constant volume. Yeah? Now, my dear students, in thermodynamics, I believe all of you would have come across a relation. And what is the relation? You should be knowing about this relation. Delta H is equal delta U plus delta NGRT. I believe you all would have come across this particular reaction. My dear students, since right now I'm talking about the reactions, so I'll write enthalpy change of the reaction, internal energy change of the reaction. This is one more result which I shall be using. This is one more result which will be relating enthalpy and internal energy of a particular reaction. This is the result which shall be relating. This is the result which shall be relating enthalpy change and internal energy change of the reaction, right? There will be some reactions whose delta U will be given to us and delta H we will be supposed to calculate. There will be some reactions whose delta H will be given to us, delta U we will be supposed to calculate. For all those questions, I shall be using this particular result, right? A particular set of questions is asked. Particular set of questions is asked in which delta U will be given, delta H you are supposed to calculate. Delta H will be given, delta U are supposed to calculate. So for those sort of questions, I'll be using this particular result over here. Okay. Now people, few more things. My dear students, based on the sign of delta H, we classify reactions into two types. Based on the sign of delta H, we classify reactions into two types. Remember it. Those reactions whose delta H is positive, what is delta H? Enthalpy change. You can call it like this: enthalpy of products minus enthalpy of reactants as well, right? Delta H, enthalpy change. You can say enthalpy of products minus enthalpy of reactants. Now, my dear students, that particular reaction whose delta H is positive, delta H positive means HP minus HR, this term is positive. When can be this particular term positive? This particular term can be only positive if enthalpy of products is greater than that of enthalpy of reactants. And let me tell you, those sort of reactions which have got delta H positive, what do you call those reactions as? You call them as endothermic reaction. You call them as the endothermic reactions. Point number one. Point number two. Those particular reactions which will be having delta H negative. That means enthalpy of products minus enthalpy of reactants. This term will come out to be negative. When can be this particular term negative? When can be HP minus HR negative? This can be only negative if enthalpy of products will be less than that of enthalpy of reactants. And those reactions for which delta H comes out to be negative, you call those reactions over here as the exothermic reactions. So my dear students, on the basis of the sign of delta H, you are going to classify the reactions into two types. One is going to be endothermic, one is going to be exothermic. For endothermic reactions, delta H is positive. For exothermic reactions, delta H is negative. Let me know once in the chats if all these things are clear. Let me know once in the chats if all these things are absolutely clear to you. Quickly in the chats, with some thumbs ups. Everyone. Quickly, my dear students. Everyone in the chats. Quickly. Everyone in the chats. Some people are saying video is not clear. You need to change your settings. I think you're watching the video at 140p, right? Just go to the settings and increase the quality of the video. Yeah? Perfect, people. So one thing which I want every one of you to know from now onwards. If I ask you anytime from now on, what is enthalpy of reaction? What you should say. Enthalpy of reaction is nothing but amount of heat absorbed or released during a chemical reaction carried out at constant pressure. Sometimes if I ask you, what is internal energy change of the reaction? You will say it is nothing but amount of heat absorbed or released during a reaction which is carried out at constant volume. If I ask you what is the result between enthalpy of the reaction and internal energy of the reaction, you will say delta H is equal to delta U plus delta NGRT. Right? Okay. I believe this is clear. On the basis of sign of delta H, we classify reactions into two types: endothermic, exothermic. Endothermic reactions are the ones whose delta H is positive. Exothermic reactions are the ones whose delta H is negative. As simple as that. Okay. Now, people, let's move ahead. My dear students, there is something which is what we call as standard enthalpy of the reaction. See, right now I defined enthalpy of the reaction. Now I'm going to define one more term, that is standard enthalpy of the reaction. Standard enthalpy of the reaction. What is meant by the standard enthalpy of the reaction? Let me make it clear to you. My dear students, standard enthalpy of the reaction is nothing but it is the enthalpy change. It is the enthalpy change. It is the enthalpy change. What is meant by enthalpy change? Enthalpy change means the amount of heat absorbed or released. Enthalpy change means the amount of heat absorbed or released. Standard enthalpy of the reaction is the enthalpy change which is measured under standard conditions. Now the point is, what are standard conditions? Standard conditions are pretty much simple here, guys. When pressure is kept as 1 atm and temperature is kept constant, which is generally taken as 25 degrees centigrade. Now what it means exactly? My dear students, imagine you have got the reaction in which reactants are getting converted into products. I believe this particular reaction is carried out at 1 atm pressure. I believe this particular reaction is carried out at 1 atm pressure. I believe this particular reaction is carried out at constant temperature as well. I believe this particular reaction is carried out at constant temperature as well. Assume that the temperature at which reaction is taking place is 25 degrees centigrade. So can I say this particular reaction is carried out under standard conditions? Absolutely, this particular reaction is carried out under standard conditions. At this point of time, whatever amount of heat will be absorbed or released during this particular reaction, that is what you call as standard enthalpy of the reaction. That is what you call as standard enthalpy of the reaction. That is what you call as standard enthalpy of the reaction. Am I clear? Am I clear, people? Am I clear? Quickly. Am I clear with this? Am I clear with this? Quickly in the chats. Yes, we are going to solve questions as well. Am I clear with this? So I took a reaction which is carried out under standard conditions. These are the standard conditions. Under standard conditions, whatever amount of heat will be absorbed or released during the reaction, that is something which you call as standard enthalpy of the reaction. Now people, if I ask you, is there any difference between these two terms? What should be your answer? Is there any difference between these two terms? Yes, there is a difference. This is something which you call as enthalpy change. What is meant by enthalpy change? The amount of heat absorbed or released. This is something which is what you call as standard enthalpy change. This is something which you call as standard enthalpy change or standard enthalpy of the reaction. Okay? Perfect. Whenever enthalpy change of the reaction is measured under standard conditions, you call that particular enthalpy change which is measured under standard conditions as the standard enthalpy of the reaction. I believe this is clear to everyone. Now people, if this is clear to everyone, then let me tell you something very, very, very important. Let me tell you something very, very, very important. You need to remember that and understand that one by one. Try to understand, people. If I talk about standard enthalpy of the reaction, which is the amount of heat absorbed or released during a chemical reaction which is carried out under standard conditions. Sometimes you call the standard enthalpy of the reaction as, sometimes you call it as standard enthalpy of formation, which I'll let you know in some time. Sometimes you call it as the standard enthalpy of combustion, which I'll let you know in some time. Sometimes you call it as standard enthalpy of neutralization, right? Okay, you would have heard about these terms, I believe. Sometimes, my dear students, you call it as enthalpy, standard enthalpy of whatever sublimation, right? Sometimes you call it as standard enthalpy of fusion, right? Sometimes you call it as the lattice enthalpy. Sometimes you call it as the lattice enthalpy. Sometimes you call it as the enthalpy of atomization, right? Sometimes you call it as, for example, enthalpy of hydrogenation. Perfect. All these different types of enthalpies of the reaction we have to discuss one by one, right? So first of all, enthalpy of the reaction under standard conditions. Simple: amount of heat absorbed or released. Amount of heat absorbed or released during a chemical reaction which is carried out under standard conditions. Okay. Now, this enthalpy of reaction, sometimes you can call it as enthalpy of formation, enthalpy of combustion, enthalpy of sublimation, enthalpy of fusion, enthalpy of vaporization, enthalpy of atomization, right? Enthalpy of hydrogenation, etc., etc. Now, all these things one by one we need to discuss, and from these questions are basically asked in your NEET examination, right? Correct? Right, people? So all these things, Abid, this is not standard condition which we do in mole concept. It's not STP. This is the standard conditions where temperature is kept constant, generally 25 degrees centigrade. Okay, remember it. Moving ahead, pressure you can keep 1 atm or 1 bar, which is approximately the same. Okay, now one by one we shall be discussing about all these enthalpies of the reaction. Try to understand, people, what exactly I'm going to talk about. Okay, try to understand what exactly I'm going to talk about. The first enthalpy of the reaction, which is what you call as enthalpy of formation. Enthalpy of formation. Enthalpy of formation. I'm representing it as delta H naught F, and I'm defining it under standard condition. Enthalpy of formation. How do we define the term enthalpy of formation? Try to understand. See, guys, I'm writing its definition. The enthalpy change, it is defined as the enthalpy change. Enthalpy change means the amount of heat absorbed or released. Enthalpy change means the amount of heat absorbed or released. The enthalpy change when 1 mole of substance, is formed, when 1 mole of substance is formed from its constituent elements, which must be present in their standard states. So before making you understand the meaning of enthalpy of formation, let's try to understand exactly what standard state of an element is all about. What is meant by standard state of an element? Let me tell you, people, standard state of an element, it is that state of an element in which element exists in nature. Right? Standard state, it is that state of the element in which element exists in nature. Right? Or we can say standard state of an element is the most stable state of the element as per thermodynamics. Now try to understand. For example, if I talk about hydrogen in nature exists as H2 gas. If I talk about nitrogen in nature exists in the form of N2 gas. Chlorine in the nature exists in the form of Cl2 gas. Bromine in nature exists in the form of Br2 liquid. Iron in nature exists in the form of Fe solid, right? So these are the These are what I call as standard states of hydrogen, nitrogen, chlorine, bromine, iron, etc. If I talk about carbon, if I talk about, for example, carbon, right? What are the two main allotropes of carbon? Two main allotropes of carbon are your diamond and graphite. Two main allotropes of your carbon are your diamond and graphite. Now, if I ask you, among diamond and graphite, which one is thermodynamically more stable? Which one is thermodynamically more stable? Graphite is thermodynamically more stable than diamond. So I would say the standard state of carbon is your graphite. Graphite is the standard state of carbon. Why? Because graphite is thermodynamically more stable, and that state of the element, that allotrope of the element, which is thermodynamically more stable, that is considered to be the standard state of the element, right? That is something which you call a standard state of the element, right? So first thing, standard state. It is that state in which element exists in nature. Number one. Number two, whenever you see an element which has got allotropes, that allotrope which is thermodynamically more stable, that will be considered as the standard state of the element. Like you have carbon. Its two main allotropes are your diamond and graphite. Thermodynamically, graphite is more stable. So graphite is something which I will be calling as the standard state of carbon. I believe this is clear to everyone. Now people, let's go on. Let's talk about our actual thing, that is standard enthalpy of formation. Look at it carefully. It is defined as the enthalpy change. Enthalpy change means amount of heat absorbed or released. So the amount of heat absorbed or released when 1 mole of the substance is formed from its constituents, which must be present in their standard states. Let's get to know what is meant by this particular definition. Try to understand, people. Just try to understand. For example, I'm writing calcium carbonate here. If I ask you, what are the constituent elements of calcium carbonate? It's calcium, it's carbon, it's oxygen. It's calcium, it's carbon, it is oxygen. What is the standard state of calcium? It is calcium solid. What is the standard state of oxygen? It is O2 gas, right? It is O2 gas. And if I ask you, what is the standard state of carbon? It is carbon graphite. Perfect. Look at this particular reaction. Is this reaction balanced or not? There are a lot of people, spammers we have. Just a second. Gone. Done. Guys, concentrate in the class, okay? Concentrate in the class. Okay? I've blocked. Keep on telling me when the spammers come, okay? Keep on telling me. Perfect, guys. If you look at this particular reaction, is this reaction balanced or unbalanced? This particular reaction right now is unbalanced. So let me balance this reaction. Let me make it as 3/2. Now is the reaction balanced? Absolutely, the reaction is balanced. My dear students, in this reaction, if you observe carefully, can I say 1 mole of calcium carbonate is being formed? Absolutely, 1 mole of calcium carbonate is being formed from its elements which are present in their standard states. 1 mole of calcium carbonate is being formed from its elements which are present in their standard states. The amount of heat absorbed or released during this particular reaction, I will be calling that as the enthalpy of formation of calcium carbonate. I told you, enthalpy of reaction, sometimes you call it as enthalpy of formation. Sometimes you call it as enthalpy of combustion, right? Okay. If you look here carefully, 1 mole of calcium carbonate is getting formed from its elements which are present in their standard states. So whatever amount of heat will be absorbed or released during the reaction, that is something which you call as enthalpy of formation of calcium carbonate. As simple as that. Let me take one more example. My dear students, for example, I'm writing NH3 gas. NH3 gas, right? I'm writing NH3 gas. If I ask you, what are the constituent elements of NH3? It's nitrogen and hydrogen. Now tell me, what is the standard state of nitrogen? It is N2 gas. What is the standard state of hydrogen? It is H2 gas. Now, is the reaction balanced? No, the reaction is not balanced yet. So let me balance it. Let's keep it as 1/2. Let's keep it as 3/2. Now the reaction is balanced. Now the reaction is balanced. My dear students, if you look at this particular reaction carefully, can I say 1 mole of NH3 is being formed? 1 mole of NH3 is being formed from its elements which are present in their standard states, right? 1 mole of NH3 is being formed from its elements which are present in their standard states. So, whatever amount of heat will be absorbed or released during this particular reaction, that is something which you will be calling as standard enthalpy of formation of NH3. As simple as that. As simple as that, right? Okay, let me take one more example. Let me take one more example. After that, I'll give you a question. Let me take one more example. After that, I'll be giving a question. For example, I'm writing here H2O liquid, right? H2O liquid, H2O liquid. Now, hydrogen, oxygen. What is the standard state of hydrogen? H2. Perfect. What is the standard state of oxygen? O2. O2. Is the reaction balanced? The reaction is not yet balanced. Now the reaction is balanced. Can I say 1 mole of water? 1 mole of water is being formed from its elements which are present in their standard states? Absolutely. So the amount of heat absorbed or released during this particular reaction is something which you call as the enthalpy of formation of water. Perfect. And my dear students, let me tell you the first reaction which you have over here. The first reaction is what you call as, this reaction is what you call as the formation reaction of calcium carbonate. This reaction is what you call as the formation reaction of NH3. This reaction is what you call as the formation reaction of water, right? Formation reaction of water, formation reaction of NH3, formation reaction of calcium carbonate. So whenever you have to write formation reaction of any substance, one thing that should strike your mind. What is that? 1 mole of substance should get formed from its elements which should be present in their standard states. Which should be present in their standard states. Okay? Perfect? Perfect, people? Perfect, people? I believe this is clear. Now I have got a question for you. I have got a question for you. I'm writing a reaction. N2 gas plus 3 times H2 gas. It gives 2 times NH3 gas. This is the reaction which I have written over here. This is the reaction which I have written over here. I am telling you, during this particular reaction, this is the amount of heat absorbed or released, which is, for example, X kilojoules. X kilojoules. X kilojoules is the amount of heat which is absorbed. Because I'm writing the delta H positive. Delta H positive means endothermic. Endothermic means heat absorbed. I believe during this particular reaction, X kilojoules of heat is being absorbed. X kilojoules of heat is being absorbed. Now you tell me, can I call this X kilojoules as the enthalpy of formation of NH3? What do you think? Can I call it as the enthalpy of formation of NH3? This is a general question from my side. A general question from my side. I'm writing a reaction over here. I wrote a reaction. Perfect. I'm telling you that X kilojoules of heat is absorbed during the reaction. Now, I am asking you whether I should call this X kilojoules as the enthalpy of formation of NH3. Is it? No, I'm not going to call it as the enthalpy of formation of NH3. Why? Why? Remember the definition. 1 mole of NH3 should get formed. Over here. Is 1 mole of NH3 being formed? No. 2 moles of NH3 are being formed. 2 moles of NH3 are being formed. Can I say when 2 moles of NH3 are being formed, how much heat is absorbed? X kilojoules. Therefore, when 1 mole of NH3 will be getting formed, this will be the heat absorbed. This will be the heat absorbed. right? This will be the heat absorbed when 1 mole of NH3 will get formed, and the amount of heat which will be absorbed or released when 1 mole of substance is getting formed, that is something which you call as enthalpy of formation. So can I say over here, can I say, my dear students, can I say, no doubt, this was the total amount of heat absorbed during the reaction. But if in equation they ask you, calculate the enthalpy of formation of NH3. So you will say enthalpy of formation of NH3 is nothing but x by 2 kilojoules per mole, right? Is it clear? Is it clear, people? Is it clear to everyone? Quickly in the chats. Quickly in the chats. Quickly in the chats. Right? Now, over here, 1 mole of calcium carbonate was getting formed. Right? And when 1 mole of calcium carbonate was getting formed, whatever was the amount of heat absorbed or released, that is something which I'm calling as enthalpy of formation of calcium carbonate. When 1 mole of NH3 was getting formed, whatever amount of heat was absorbed or released during the process, that is something which I was calling as enthalpy of formation of NH3. 1 mole of water was getting formed. Whatever heat was absorbed or released during this process, that is something which I am calling as enthalpy of formation of water. But over here, 2 moles of NH3 was getting formed. At this point, was enthalpy of reaction equal to enthalpy of formation? No. So can I generalize a statement? Can I generalize a statement? Can I say enthalpy of the reaction and enthalpy of formation can only be equal when 1 mole of the substance, would be getting formed? When 1 mole of the substance would be getting formed? When 1 mole of the substance would be getting formed from its elements which would be present in their standard states. Is this statement clear? Is this particular statement clear? Is this particular statement clear? Let me know in the chats quickly. Everyone. Everyone in the chats. Everyone in the chats. So enthalpy of formation and enthalpy of reaction will be only equal when 1 mole of the substance will be getting formed. Okay? Perfect. Now, there is one more thing which you need to remember directly from now on. Do remember the standard enthalpy of formation. The standard enthalpy of formation of an element present in its standard state. The standard enthalpy of formation of an element present in its standard state is taken as 0. This is one more thing which you have to remember. What is meant by that? For example, I'm writing standard enthalpy of formation of H2 gas. Okay. For example, I'm writing standard enthalpy of formation of O2 gas. For example, I'm writing standard enthalpy of formation of graphite. Now look at these examples carefully. H2 gas, it is the standard state of hydrogen. This is the standard state of oxygen. This is the standard state of carbon. And standard enthalpy of formation of an element in its standard state is taken as 0. Is taken as 0. Is taken as 0. Clear? I've got one question for you. Which of the following reactions define the standard enthalpy of formation? Which of the following reactions define the standard enthalpy of formation? Can you let me know in the chats? Look at all these reactions carefully. Look at all these reactions carefully and let me know the answer of this question. It's an asked question, guys. It's an asked question. It's an asked question. Quickly. How do you define the enthalpy of formation? In order to define the enthalpy of formation, 1 mole of substance has to get formed. 1 mole of substance has to get formed. Over here, 1 mole of substance is being formed. Over here, 1 mole of substance is being formed. Over here, 1 mole of substance is being formed. But here, 1 mole of the substance, no, 2 moles of the substance are being formed. So cross it first of all. Cross it first of all. Now, 1 mole of the substance has to get formed from its elements which must be present in its standard states. What is the standard state of carbon? The standard state of carbon is graphite, but here you have used diamond. So no, this is not the case. Look at this one. What is the standard state of carbon? Standard state of carbon is graphite. Over here you have used carbon monoxide. This is not the case. Look at the second example. What is the standard state of hydrogen? H2. What is the standard state of chlorine? F2. So this is going to be the correct answer of this particular question. Am I clear to everyone? Am I clear to everyone? Absolutely, it's going to be option B, which is going to be the correct answer of this particular question. Yeah? I believe it's absolutely clear. Now, my dear students, let me, before showing you one more question, let me tell you one more important thing. What is that? That is calculation of standard enthalpy of reaction from standard enthalpy of formations. Calculation of standard enthalpy of reaction from standard enthalpy of formations. Look at it carefully again. Look at it carefully again. For example, I'm writing a reaction. The reaction is like this. N1A plus N2B, it gives N3C plus N4D. Imagine this is a balanced chemical equation wherein N1, N2, N3 and N4. These are the stoichiometric coefficients of reactants and products. N1, N2, N3, N4. These are the stoichiometric coefficients of reactants and products. Okay? Stoichiometric coefficients of reactants and products. Now, my dear students, for example, I need to calculate the amount of heat which is being absorbed or released during this reaction. That means I'm asking you to calculate the enthalpy of the reaction, the standard conditions. How do we do it? How do we do it? It is always equaled. It is always equaled. The standard enthalpy of formation of products minus the standard enthalpy of formation of reactants. It is always equaled. Standard enthalpy of formation of products minus standard enthalpy of formation of reactants. How do I write it? Try to understand. Start with the product. Its stoichiometric coefficient is N3 multiplied by standard enthalpy of formation of C plus stoichiometric coefficient here is N4 multiplied by standard enthalpy of formation of D, right? This whole term is what I'm calling as standard enthalpy of formation of products minus standard enthalpy of formation of reactants. Start with A. Its stoichiometric coefficient is N1 multiplied by the formation of A plus it is N2 multiplied by standard enthalpy of formation of B. My dear students, do remember this particular result as well. From this particular result, you can solve a lot of questions. From this particular result, you can solve a lot of questions. From this particular result, you can solve a lot of questions. This is the general result by means of which you can calculate the standard enthalpy of reaction from the standard enthalpy of formations of products and reactants. And it is written as standard enthalpy of formation of products minus standard enthalpy of formation of reactants. In the questions, they will give you these values. In the questions, they'll give you these values, right? They'll give you these values. Okay, they'll give you these values. Number one. Number two, if you ask me, what is the unit of the standard enthalpy of the reaction? It is majorly expressed as kilojoules per mole, right? It is majorly expressed in kilojoules per mole. Now, I'll show you a question and this concept will be clear there only. I'll show you one question in which the concept will be clear. It will be absolutely clear. One question I'm going to show you. Okay? Look at this question carefully. Read the question carefully. Again, I'm telling you the same thing. Standard enthalpy of reaction is equal to standard enthalpy of formation of products minus reactants. But take into consideration the stoichiometric coefficients as well. Okay? Look at this question carefully. The standard enthalpy of formation of carbon dioxide, carbon monoxide and water are given as this respectively. The heat exchanged by the reaction at constant volume. The heat exchanged by the reaction at constant volume at standard conditions in kilojoules for the reaction is. See guys, how exactly am I going to solve this question? First thing, I'm going to write the reaction again. The reaction is like this. Carbon dioxide gas plus H2 gas. It gives carbon monoxide gas plus H2O gas. This is the reaction that's given to me. Agreed? This is the reaction that's given to me. As per the question, if you look carefully, what am I supposed to calculate? I'm supposed to calculate the heat absorbed or released during the reaction at constant volume. Heat absorbed or released during the reaction at constant volume. That means this is the thing which I'm supposed to calculate. This is the thing which I'm supposed to calculate. Heat absorbed or released during the reaction at constant volume. And what do you call this as? I hope you remember. That's something which you call as internal energy change in the reaction. And since I'm supposed to calculate it under standard conditions, so basically this term I'm supposed to calculate. Internal energy change of the reaction I'm supposed to calculate basically, right? Internal energy change of the reaction I'm supposed to calculate. Correct? Now try to understand carefully. I told you already. There is a relation between delta H and delta U. There is a relation between delta H and delta U. Do you remember that? Delta H is equal to delta U plus delta NGRT. Now, my dear students, can you let me know what is the value of delta Ng for the reaction? What is delta Ng first of all? Delta Ng represents number of moles of gaseous products minus the number of moles of gaseous reactants. Number of moles of gaseous products minus number of moles of gaseous reactants. Now, this is the gaseous product, this is the gaseous product, this is the gaseous reactant, this is the gaseous reactant. Number of moles of gaseous products. So 1 plus 1, that makes it 2. So number of moles of gaseous products are 2 minus number of moles of gaseous reactants. 1 plus 1, that's 2. So 2 minus 2 is 0. So my dear students, this is the reaction whose delta Ng is 0. If the delta Ng for the reaction is 0, you know delta H is equal to delta U plus delta NGRT, right? Delta NGRT. And if you want to write it under standard conditions, you can write it too. Now, since delta Ng for the reaction is 0, so I would say delta H for the reaction is nothing but delta U for the reaction. Perfect. So basically, I'm supposed to calculate delta U for the reaction, and I got to know delta U for the reaction is nothing but delta H. So indirectly, I'm supposed to calculate delta H for the reaction. Indirectly, I'm supposed to calculate standard enthalpy change of the reaction. And already I have told you, standard enthalpy of the reaction can be calculated with the help of standard enthalpy of formation. With the help of standard enthalpy of formation, I just need to write standard enthalpy of formation of products minus standard enthalpy of formation of reactants, right? So start with the products. Stoichiometric coefficient is 1, right? So leave it as such, multiplied by standard enthalpy of formation of what? Carbon monoxide plus 1 multiplied by standard enthalpy of formation of what? Standard enthalpy of formation of water. Perfect. So this is your product side minus the reactant side. Look here, stoichiometric coefficient is 1 multiplied by standard enthalpy of formation of what? Standard enthalpy of formation of carbon dioxide plus this is stoichiometric coefficient is 1 multiplied by standard enthalpy of formation of H2. Yes, it's H2. Correct, people? Now, if you look at this particular equation carefully, what about this particular term? Standard enthalpy of formation of H2 gas. H2 gas is the standard state of hydrogen, and the standard enthalpy of formation of an element which will be present in its standard state, it is taken as 0. So this term is 0. This term is 0, right? This term is 0. This term is given to you as per the equation of carbon monoxide. Even this term is given to you as per the equation, enthalpy of formation of water, right? Even this term of carbon dioxide, this is given to you. Put the values here and get the answer. That's all. That's all. You will be getting the delta H of the reaction. And delta H of the reaction is nothing but delta U for the reaction. As simple as that. Right? As simple as that. And the final answer of the question after solving this will come out to be 41.2 kilojoules per mole. I believe this is clear. If this is clear, let me know once in the chats with some thumbs ups. Quickly, guys. Quickly, everyone in the chats. Everyone in the chats. Everyone in the chats, quickly. And I can see everyone has not liked the video yet. I want you guys to smash that like button as well, quickly. Perfecto. Perfect, guys, perfect. I'm moving ahead. I am moving ahead. I believe the first enthalpy of the reaction, which was called as enthalpy of formation, that is clear. Now moving on to the second, that is standard enthalpy. Standard enthalpy of combustion. Now this is something which you will understand easily, guys, very easily. Okay, so first thing, I'm representing this with delta H naught C. Now what this standard enthalpy of combustion is all about. Let me write its definition. My dear students, standard enthalpy of combustion, it is defined as the enthalpy change. It is defined as the enthalpy change. What is meant by enthalpy change? The amount of heat absorbed or released. What is meant by enthalpy change? The amount of heat absorbed or released. Right? Okay. The enthalpy change. When 1 mole of substance undergoes combustion. When 1 mole of the substance undergoes combustion in excess of oxygen. When 1 mole of the substance undergoes combustion in excess of oxygen. First of all, before making you understand this particular definition, let me tell you, combustion, it is always an exothermic process. If combustion is always an exothermic process, that means during combustion, heat is always released. Therefore, that is the reason why enthalpy of combustion value always comes out being negative. That is the reason why delta H naught C is always negative, because it's always exothermic. Right? Okay. Now people try to understand what it means. Have a look. Carefully have a look. My dear students, for example, I'm writing a reaction. Understand it like this. CH4 plus O2 gas. It gives your carbon dioxide and water. This is the reaction, a general reaction I have written. Tell me one thing, is this reaction balanced or not? I don't think this reaction is balanced. This reaction needs to be balanced. Right? So make this 2 times. Make this 2 times. Now the reaction is balanced. This is 1 here. This is 1 here. Okay? If you look at this reaction carefully, first of all, it is the example of combustion reaction. You have taken a hydrocarbon. You are doing its combustion. And combustion of hydrocarbon, it leads always to the formation of carbon dioxide and water. Its products are always carbon dioxide and water. Now people tell me one thing. Can I say in this particular reaction, 1 mole of substance is undergoing combustion? Do you see? 1 mole of substance undergoing combustion. Right? During combustion, heat is always released. So can I say whatever amount of heat will be released during this particular process, that is something which you will be calling as enthalpy of combustion of CH4. Right? Okay? Whatever amount of heat will be released during this particular process, that is something which you will be calling as standard enthalpy of combustion of CH4. Correct? Because 1 mole of substance has undergone combustion. Look at the definition. The enthalpy change when 1 mole of substance undergoes combustion. Whatever heat is released during that process, that is something which you call as standard enthalpy of combustion. So this is standard enthalpy of combustion of your CH4. Agreed? Right, people? For example, I'm taking, let's say, C3H8. I'm doing its combustion. It always leads to the formation of carbon dioxide and water, right? Balance this reaction. This is 3 times, this is 3 times, right? Make it 4 times and make it 5 times. The reaction is balanced. If you look at this particular reaction carefully, can I say 1 mole of propane is undergoing combustion? 1 mole of substance is undergoing combustion. The amount of heat released when 1 mole of propane undergoes combustion, that is something which I'll be calling as standard enthalpy of combustion of your propane. Correct? Right? Now people tell me one thing. If I write the reaction like this, 2 times CH4 plus 4 times O2 plus 2 times carbon dioxide plus 4 times water, right? Plus 4 times water. For example, I'm telling you that standard enthalpy of this particular reaction is minus 100 kilojoules. I'm asking you to calculate the standard enthalpy of combustion of CH4. Can you do it? I gave you the reaction, a balanced reaction, right? I'm telling you, enthalpy change of this reaction is equal to minus 100 kilojoules. I'm asking you to calculate enthalpy of combustion of CH4. Can you do it? See guys, in this reaction, look carefully. 2 moles of methane are undergoing combustion. So when 2 moles of methane are undergoing combustion, how much heat is released? 100 kilojoules. So when 1 mole of methane will undergo combustion, how much heat will be released? 50 kilojoules. Can I say enthalpy of combustion of methane will be minus 50 because heat is being released, right? If you look carefully, here 1 mole of methane was undergoing combustion. Here 1 mole of propane was undergoing combustion. And in both these reactions, where 1 mole of substance was undergoing combustion, in both these reactions, if you see, enthalpy of reaction and enthalpy of combustion, they are equal. But in the last case, is the enthalpy of reaction and enthalpy of combustion equal? They are not equal. So can I generalize a statement? Can I say enthalpy of the reaction will be only called as the enthalpy of combustion when 1 mole of substance will be undergoing combustion? When 1 mole of substance will be undergoing combustion? If this is clear, let me know once in the chats with some fire emojis. Everyone, people. Everyone means everyone. Is it clear? Is it clear, people? Okay. One more thing which I want to tell you over here. One more thing which I would want to tell you. Look at it very carefully. Okay? Right? Look at it very carefully. I'm writing the reaction. H2 gas plus O2 gas. It gives me H2O liquid. Let's assume the enthalpy change of the reaction is delta H naught R. This is the amount of heat which is absorbed or released. Right? It can be anything. Look carefully. My dear students, do you see 1 mole of H2 is undergoing combustion? Right? 1 mole of H2 is undergoing combustion. And when 1 mole of substance undergoes combustion, standard enthalpy of reaction, this will be also called as standard enthalpy of combustion of H2. Look at one more thing. Do you see 1 mole of water being formed? 1 mole of water being formed from its elements which are present in their standard states. When 1 mole of substance is getting formed At that point of time, delta HR is also equal to delta H naught F. So can I say this is something which I'll be calling as standard enthalpy of formation of water as well? If this particular point is clear, then you are fit enough to solve the questions. Let me know in the chats if this is clear. Let me know in the chats if this particular point is clear to everyone. Quickly in the chats, everyone. All clear? All clear? I want everyone to say it, guys. This is something which is very important. This is something which is very important. 1 mole of substance is undergoing combustion, right? And 1 mole of substance is being formed as well. Correct? Right? And I've told you already, when 1 mole of substance is formed from its elements present in their standard states at that point of time, standard enthalpy of reaction is called as standard enthalpy of formation. Formation of what? Formation of water. Or you can say 1 mole of H2 is undergoing combustion. So you can say standard enthalpy of reaction will be also called as standard enthalpy. Standard enthalpy of reaction will be also called as standard enthalpy of combustion of H2 over here. Okay. Perfect. I believe this particular point is absolutely clear to everyone. And if this point is clear to everyone, let me tell you one more thing from which you can get the questions. My dear students, take a note of this, okay? Take a note of this. For example, I've got the reaction N1A plus N2B gives N3C plus N4D. This is a balanced chemical equation wherein N1, N2, N3, N4, these are the stoichiometric coefficients of the reactants and products, right? Now, my dear students, if I ask you how much amount of heat is absorbed or released during the reaction, how much amount of heat is absorbed or released during the reaction, one way of solving this is going to be enthalpy of formation of products minus enthalpy of formation of reactants. One way of getting this. One way of calculating standard enthalpy of reaction. What is that? Formation of products minus formation of reactants. But there is one more way as well. It is going to be combustion of reactants minus combustion of products. It is going to be combustion of reactants minus combustion of products. How exactly you are going to write it? Here now you are going to start with reactants. This is your reactant, this is your reactant. Stoichiometric coefficient N1. So N1 multiplied by standard enthalpy of combustion of A plus N2 multiplied by standard enthalpy of combustion of B. This is what I am calling as standard enthalpy of combustion of reactants minus standard enthalpy of combustion of products. So start with the product. Stoichiometric coefficient is N3. So N3 multiplied by standard enthalpy of combustion of C plus N4 multiplied by standard enthalpy of combustion of D. This is one more way of calculating the standard enthalpy of the reaction. This is one more way of calculating the standard enthalpy of reaction. First one, standard enthalpy of reaction is equal to standard enthalpy of formation of products minus reactants. Also, it can be calculated as standard enthalpy of combustion of reactants minus products. Okay, remember it directly. And if you could remember it directly, it is the time to solve one question. And this is again the asked question. This has been asked in your examination. I don't remember exactly whether this was asked in mains, JEE mains or Neet. Look at this. Look at it carefully. Look at it carefully, guys. The heat of combustion of ethanol is minus 300 kilocalories. If the heat of formation of carbon dioxide and water are this and this, calculate the heat of formation of ethanol. We are supposed to calculate the heat of formation of ethanol. We are supposed to calculate the heat of formation of ethanol. And we are already given with a reaction. Reaction is given to us. One reaction is given to us. No, Gokul, Pankhudi ma'am, she did not leave Unacademy. She is the part of Unacademy. She is taking the batches. She is taking the internal batches. Right? She is taking the internal batches. Look Look at this, people. Quickly, quickly, quickly. If you look at this particular reaction which is given to us, try to understand carefully. Can we say 1 mole of ethanol is undergoing combustion? Absolutely. 1 mole of ethanol is undergoing combustion. And when 1 mole of substance undergoes combustion, at that point of time, standard enthalpy of reaction is also called as standard enthalpy of combustion. Of what? Of ethanol. Is this standard enthalpy of combustion of ethanol given? Yes, it's given. It's given as minus 300 kilocalories. Right? The question is done. It is given as minus 300 kilocalories. 1 mole of substance is undergoing combustion. Correct? So, standard enthalpy of reaction will be called as standard enthalpy of combustion of what? Of ethanol. Now, people, tell me one thing. Delta H naught R, standard enthalpy of reaction. Can I write it as standard enthalpy of formation of products minus standard enthalpy of formation of reactants? Can I do that? I can do that. Standard enthalpy of formation of products. Start with this. So it is 2 times the standard enthalpy of formation of carbon dioxide plus this is 3 times the standard enthalpy of formation of water. Right? So this is the standard enthalpy of formation of products minus now the reactants. 1 multiplied by standard enthalpy of formation of ethanol, perfect, plus 3 times the standard enthalpy of formation of O2. Right? Right, people? Now tell me one thing. What is this delta H naught R all about? It is equal to minus 300. So this term is equal to minus 300 is equal to 2 multiplied by enthalpy of formation of carbon dioxide should be given to us. It is 2 multiplied by. It is 2 multiplied by. Enthalpy of formation of carbon dioxide is given to us as how much? Minus 94.3. Minus 94.3. Okay? Plus 3. Enthalpy of formation of water is also given to us. How much? Minus 68.5. Perfect. Minus 68.5. Minus standard enthalpy of formation of ethanol we have to calculate. Tell me one thing. What about this term? Can I say oxygen here is in standard state? Oxygen is present in its standard state. And standard enthalpy of formation. Standard enthalpy of formation of an element present in its standard state, that has to be 0. Right? So my dear students, all these things are given to us. All these things are given to us. Perfect. We are just supposed to calculate this particular term. Can't we do a bit of calculation plus minus here? Right? Can't we do a bit of plus minus here? Is it clear, people? Is it clear? Is that clear to everyone? Quickly, 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 quickly. And when you solve this, this is the answer which you get. Minus 941 kilocalories. One simple question for you. Let me see if you can solve this or not. Look at this question carefully. Look at this question carefully, guys. The heat of combustion of sucrose. The heat of combustion of sucrose is 1350 kilocalories. How much of heat will be liberated when 17.1 grams of sucrose is burnt? What do you think? What do you think? How you are going to solve this question? It's simple again. It is again simple, guys. It is again simple. Look at it carefully. Look at it carefully. As per the question is concerned, the heat of combustion of sucrose, the heat of combustion of sucrose is 1350 kilocalories. What does that mean? That means when 1 mole sucrose, that means when 1 mole sucrose undergoes combustion, how much heat is released? As per the question, it is these many kilocalories. Heat of combustion of sucrose is given. That means when 1 mole sucrose undergoes combustion, this much heat is released. But as per the question, 17.1 grams of sucrose are undergoing combustion. 17.1 grams of sucrose are undergoing combustion. That means how many moles of sucrose are undergoing combustion? Mass of sucrose divided by molar mass of sucrose. So 1 by 20 moles. 1 by 20 moles of sucrose are undergoing combustion as per the question. We know when 1 mole sucrose undergoes combustion, this much amount of heat is released. So when 1 upon 20 moles of sucrose when 1 upon 20 moles of sucrose undergoes combustion, how much heat will be released? I believe this will be 1350 multiplied by 1 upon 20. The value comes out to be how much? In the chats, people are saying 67.5. So 67.5 kilocalories of heat will be released. Isn't this something which I was supposed to calculate? Isn't this something which I was supposed to calculate? This is the amount of heat which is released when 1 by 20 moles of sucrose undergoes combustion. This is the amount of heat which is released when 17.1 grams of sucrose are undergoing combustion. I hope this is clear to everyone. I hope this is clear to everyone. Right? Okay. The question is saying how much heat will be liberated. This much amount of heat will be liberated. Right? This much amount of heat will be liberated. Okay? Right? Is it clear, people? Let me know once in the chats if it is clear, if it is super clear. Quickly. Have you heard about something called as calorific value? In bio, you would have used this term many a times. In bio, you would have used this term many a times. Calorific value. Calorific value. CV. CV, calorific value. How do you define the term calorific value? How do you define the term calorific value? Dear students, let me first of all write its definition, then I'll make you understand what this calorific value exactly is all about and where it's used. Where it's used. Calorific value. It is defined as the amount of heat released. The amount of heat released or liberated. The amount of heat liberated when 1 gram of fuel, when 1 gram of fuel undergoes complete combustion. When 1 gram of fuel undergoes complete combustion. When 1 gram of fuel undergoes combustion. When 1 gram of fuel undergoes combustion, the amount of heat released at that particular point of time is something which you call as calorific value. Is something which you call as calorific value. Can I say more the calorific value of the fuel? Can I say more the calorific value of the fuel? Comma more the heat released? More the heat released? And if more the heat released, I'll say better is the quality of the fuel. Better is the quality of the fuel. So basically on the basis of CV value, basically on the basis of CV value, you can check the quality of the fuel. You can check the efficiency of the fuel. Better is the quality of the fuel, or you can say more is the fuel efficiency. More is the fuel efficiency. More is the fuel efficiency. Now let me make you understand this particular thing here. See, understand. During combustion, heat is released. When 1 gram of fuel undergoes combustion, whatever amount of heat is released, that's something which you call as calorific value. More the calorific value of the fuel, more will be the heat released when the 1 gram of fuel undergoes combustion. More the heat released, that means more is the efficiency of the fuel, better is the quality of the fuel. Right? Now people, try to understand it a bit more in detail. Try to understand it a bit more in detail. For example, my dear students, I'm writing the standard enthalpy of combustion of methane is equal to, I'm giving the random value. It is minus 100 kilojoules per mole. It is minus 100 kilojoules per mole. If I ask you what it means, standard enthalpy of combustion of methane is minus 100 kilojoules. What it means? It means that, as per definition, it means that when 1 mole methane undergoes combustion, 100 kilojoules of heat is released. When 1 mole methane undergoes combustion, 100 kilojoules of heat is released. Right? When 1 mole methane undergoes combustion, 100 kilojoules of heat is released. That is the meaning of this particular thing, right? That is the meaning of this particular thing. Now, can you let me know what is the mass of 1 mole of methane? Mass of 1 mole of methane means molar mass of methane. How much that is? 16 grams. So instead of 1 mole of methane, I can write when 16 grams of methane undergoes combustion, 100 kilojoules of heat is released. Right? Now people, you tell me. When 16 grams of methane undergoes combustion, this much is the amount of heat released. Now tell me, when 1 gram methane undergoes combustion, when 1 gram methane undergoes combustion, use the unitary method. When 1 gram methane undergoes combustion, the heat release will be 100 divided by 16 kilojoules. 100 divided by 16 kilojoules. And people, if you look at the statement carefully, when 1 gram methane undergoes combustion, this is the amount of heat released. As I told you, the amount of heat released when 1 gram of fuel undergoes combustion, that determines the CV value of the fuel. So indirectly, I calculated the CV of methane. I calculated CV of methane. This is the calorific value of methane, 100 by 16. This is the amount of heat which is released when 1 gram of methane was undergoing combustion. Okay. Now guys, do we have to do all the process every time? No. Why I did it? Just to get you a formula. Just to get you a direct formula. Okay. Calorific value of a fuel is always equal. If you look at this is basically a calorific value. This is calorific value of methane. What was 100? 100 was magnitude of enthalpy of combustion of methane. What was 16? 16 was the molar mass of methane. So the formula of calorific value will be mod of standard enthalpy of combustion of a fuel divided by molar mass of the fuel. This is the general expression by means of which you can calculate the calorific value of the fuel. Right? General expression. Thank you, Devika. Thank you so much. This is the general expression by means of which you can calculate the calorific value of the fuel. Standard enthalpy of combustion of fuel ka magnitude divided by molar mass of the fuel. You know, more the CV, more the calorific value of the fuel, better is the quality of the fuel, more is the efficiency of the fuel, more is the heat released when 1 gram of fuel undergoes combustion. As simple as that. As simple as that. Now, my dear students, if calorific value is clear, you should be in a position to answer this question as well. You should be in a position to answer this question as well. Isn't it very simple? Enthalpies of combustions of ethane, ethene, butane, octane are given. Arrange them in the order of their fuel quality. Arrange them in the order of their fuel quality. So what do? I will be calculating the calorific value of everyone. How do you calculate the calorific value? How do you calculate the calorific value? So first of all, for example, I am calculating the calorific value of ethane, right? It will be equal to standard enthalpy of combustion of ethane, right? Divided by its molar mass, right? Sorry. Okay, what about this term? This term, it's given to us as minus, so I'll take 20 kilojoules divided by molar mass of ethane, 12 to 24, 24 plus 6 is 30. So this is basically your calorific value of ethane. Similarly, you'll calculate calorific value of every fuel, right? Then you'll compare whose calorific value is more. The one which has got more calorific value, that is going to have the better quality. I hope this is clear to everyone. If this is clear, let me know once in the chats quickly. If it is clear, let me know once in the chats quickly, people. Quickly. I'll give you on my Telegram, t.me/WASSIMSIRCHEM, right? I'll send you the PDF of this particular session in this Telegram, okay? All right, people, look at this particular question carefully. Calculate the enthalpy of combustion of C2H6. Calculate the enthalpy of combustion of C2H6. Calculate the enthalpy of combustion of C2H6. Oh my God, what did I do? Calculate the enthalpy of combustion of C2H6. Okay. So first of all, since we have to calculate the enthalpy of combustion of C2H6, tell me one thing. Can we write the combustion reaction of C2H6? We can. Can we write the combustion reaction of C2H6? We can write the combustion reaction of C2H6, right? And combustion of your hydrocarbon, it always leads to the formation of what? It always leads to the formation of your carbon dioxide. And with carbon dioxide, you will write H2O as well, water as well, right? You will write water as well. Okay. This is your combustion reaction of what? This is your combustion reaction of C2H6. Perfect. Perfect. What am I supposed to calculate? What am I supposed to calculate? I'm supposed to calculate the enthalpy of combustion of C2H6. First of all, is the reaction balanced? No. Balance the reaction. This 2 times. This has to be 2 times. This is 6. So this has to be 3 times. And this will be how much? This will be how much? 2 plus 6 by 4. This will be 7 times, I believe. You check it once. This is 7 to 14. No, not 7 times. I have done some mistake. Just a second. This won't be 7 times. How much this will be? It is x plus y divided by 4. 4 to 8. 8 plus 6 divided by 4. So it's 14 divided by 4, which is 7 by 2. Okay, this is 7 by 2. Now you must be thinking, how did I get the stoichiometric coefficient here? You must be thinking about that, right? If you do not know, let me quickly tell you. Whenever you have got the hydrocarbon in this manner, CXHY, and you are doing its combustion, when you're doing its combustion, it will first of all give you carbon dioxide and water. Now there is a general way of balancing it. General way. If this is X, take this X here. This is Y, make Y by 2 here. And what is the coefficient of oxygen here? It will be X plus Y divided by 4. This will be the stoichiometric coefficient of oxygen. If you do not know, this is how you balance it. Now, if you do not know one more thing, for example, you have got something like this, CXHYOZ. You are doing its combustion, right? You are doing its combustion. It will give you carbon dioxide, and with carbon dioxide, it will give you water as well, right? How do you balance this? X, make this X here. This is Y. Keep this Y by 2 here, right? And what about the coefficient of O2? It's X plus Y divided by 4 minus Z by 2. This is how you are going to balance it, right? This is how you are going to balance it. That's all. That's all. That's all. That's all. Perfect. Perfect. Do remember this particular thing. Do remember this particular thing. Now, people, let's have a look on the question now. Let's have a look on the question. If you look at the reaction, can I say 1 mole of ethane is undergoing combustion? Right? 1 mole of ethane is undergoing combustion. And when 1 mole of substance undergoes combustion, I'll say enthalpy of reaction is what you call as enthalpy of combustion of C2H6. Right? This is something you can write. Because 1 mole of substance is undergoing combustion. 1 mole of substance is undergoing combustion. Now, my dear students, look at all the data. I'm given with standard enthalpy of combustion of H2, combustion of CH4, combustion of C3H8. That's given to me. That's given to me. Wait. I hope this particular point is clear. Perfect. So guys, I hope this point is clear because this is something which is very important. Now look at the reaction. The enthalpy change of the reaction. The reaction is given as C3H8 plus H2. It gives C2H6 plus CH4. This is the reaction that's given to me. The reaction is given in the balanced format, right? The reaction is given in the balanced format. As per the question, the enthalpy change of the reaction. The enthalpy change of the reaction is given. How much it's given? It's given to me as minus 55.7 kilojoules per mole. Now, my dear students, how do I write enthalpy of reaction? I can write enthalpy of reaction as enthalpy of combustion of reactants minus enthalpy of combustion of products. So start with the reactants. It's going to be enthalpy of combustion of C3H8 because its stoichiometric coefficient is 1, right? Plus enthalpy of combustion of H2 because its stoichiometric coefficient is also 1. So this is the enthalpy of combustion of reactants minus enthalpy of combustion of products. So this is your enthalpy of combustion of your C2H6 plus enthalpy of combustion of your CH4, right? My dear students, this particular term, its value as per the question is minus 55.7. Now look at this particular equation. Look at this particular equation. Enthalpy of combustion of C3H8 is given to me. This term is given. Enthalpy of combustion of H2, enthalpy of combustion of H2 is given to me. Enthalpy of combustion of CH4, for CH4, it is given to me. Can't we calculate from this particular equation? Can't we calculate the enthalpy of combustion of C2H6? Absolutely. That is something which I was supposed to calculate basically. That is something which I was supposed to calculate. I believe this is clear. I believe this is clear. Perfect. I believe this is clear. Guys, let me repeat it again. I'm going to cover each and every chapter in this particular 45 days crash course which has started today. Yes? Perfect. So this sort of equation, I hope you can easily solve from now on. Now, have you heard about Hess's law? Have you heard about Hess's law? Tell me that. Say it in the chats. Have you heard about Hess's law? You would have heard, right? You would have. I'm pretty much sure. From Hess's law, confirmed equation comes. Only few things you should know about Hess's law, you're done, you're sorted, right? Look at the statement. According to this law, the net enthalpy change will be the same. The net enthalpy change will be the same if the reaction is carried out in a single step or more than one steps. First of all, tell me whether enthalpy is a state function or path function. Do you know about that? Enthalpy. Enthalpy is a state function. If enthalpy is a state function, that means it is path independent. It is path independent. You should know it. Enthalpy, that's a state function. It is path independent. Now, people, see what Hess's law is all about. For example, I've got a reaction which is carried out in a single step. Imagine this reaction is carried out in a single step, right? Imagine this reaction is carried out in a single step. A gives B. Enthalpy change over here, for example, is delta H1. Now, the same reaction is carried out in more than one steps. For example, first A gets converted into C, then C gets converted into D, then D gets converted into B. Perfect. My reaction was A to B. This is my reaction, A to B. First, it's a single step, then a series of steps. I made the reaction happen through two paths. Single step path, multi-step path, right? Now, A gives C. Let's say its enthalpy change is delta H2. C gives D, delta H3, delta H4. What is Hess's law all about? Look at the statement. Hess's law says that, enthalpy is a state function. It is path independent. So the net enthalpy change during the process will remain same. The net enthalpy change will be the same if the reaction is carried out in one step or more than one step. What does that mean? That means whatever will be the value of delta H1, that will be equal to delta H2 plus delta H3 plus delta H4. That's all. Isn't it simple, people? Isn't it simple? Whether you want to carry out this reaction in one step or more than one step, right? Enthalpy change will always remain the same. Enthalpy change will always remain the same. Yeah? Enthalpy change will always remain the same. Perfect. It is independent of the path. Now, few more things which I want you guys to remember. For example, take a note of these things. I'll use these things in a while. For example, you have got the reaction like this. A gives B. Let's say its delta H is some X kilojoules. Its delta H, for example, is X kilojoules. My dear students, if you multiply or leave multiplication aside, if you reverse this reaction, when you reverse this reaction, you have to change the sign of delta H. Now the delta H of this reaction will be minus X kilojoules. minus 6 kilojoules. For example, I'm multiplying this reaction by some number. For example, I'm multiplying this reaction by n. Na gives Nb. I multiplied this reaction by n. This n has to be multiplied with its delta H value as well. So I'll say delta H for this reaction will be n times x. N times x. Okay, n times x. Okay. So first thing, when you reverse the reaction, delta H sign has to be inversed. Delta H sign has to be changed. When you multiply a reaction by some number, that number has to be multiplied with its delta H as well. Okay. Now, my dear students, when you add some reactions, their delta H values are to be added to. I'll write it over here. For example, you have got a reaction A plus B gives C plus D. Then you have got the reaction E plus F gives X plus Y, right? For example, the first reaction, its delta H is delta H1. Here it's delta H2. If I add these two reactions, after adding these two reactions, I'll get a net reaction. If I ask you, what will be the enthalpy change of the net reaction? Since you added these two reactions, so the enthalpy change of the last reaction will be delta H1 plus delta H2. Is it clear? When you add two reactions, their delta H values are to be added to. That's all. Their delta H values are to be added to. Now, for example, I'm giving you a very small question. Let me see if you can solve this or not. Let's say I've got the reaction carbon graphite plus half of O2 gas. Let's say it gives carbon monoxide gas. I'm giving you some random values. Let's say delta H for this reaction is equal to minus 100 kilojoules. For example. Now, carbon monoxide plus half of O2. It gives you carbon dioxide. Imagine its delta H is, for example, some random values. Minus 200 kilojoules. Now, 2 times carbon dioxide gives 2 times carbon graphite plus 2 times O2. You're supposed to calculate delta H for this particular reaction. Can you give it a try? People? Can you give it a try? This will be the type of the question which will be asked. A very simple and basic question. My dear students, the reaction whose delta H is to be calculated. Remember it in short. The reaction whose delta H is to be calculated. You need to make that reaction out of the given reactions. Right? The reaction whose delta H is to be calculated, you have to make that reaction out of the given reactions. Now, how will you make this reaction? Tell me that. How will you make this reaction? Let me call this as equation 1. Let me call this as equation 2. Let me call this as equation 3. How will you make equation 3? My dear students, the first thing which I'll do, for example, if I add first and second. When I add first and second, this and this gets cancelled. So I'll be getting carbon graphite plus half of O2 makes it 1 times O2, gives carbon dioxide. Since I added these two reactions, so their delta H values are to be added to. So it will be minus 100 plus minus 200, right? And this will be minus 300. Perfect. Now guys, think over it. If I multiply this reaction by number 2, that 2 has to be multiplied with this as well. So it will be minus 600. Now, if I reverse this reaction, it will be something like this, right? And when I reverse the reaction, the sign of delta H has to be changed. So it will be plus 600 kilojoules. Look at this reaction carefully. My dear students, look at this particular reaction carefully. Were we supposed to make the same reaction? Just try to compare these two reactions. Absolutely, these two reactions are same, right? So can I say I made the reaction by certain operations, right? And I got the delta H, which I was supposed to calculate. I believe it's clear. I believe it's clear. For example, one question I'm giving you. Look at this question, guys. We are given with certain reactions, their delta H values are given. What are we supposed to calculate? What are we supposed to calculate? We are supposed to calculate the enthalpy of formation of H2O2. We are supposed to calculate the enthalpy of formation of H2O2. Look at it carefully. First of all, we are supposed to calculate the enthalpy of formation of H2O2. Will you be able to write the formation reaction of H2O2 on your own? Will you be able to write the formation reaction of H2O2 on your own? In order to write the formation reaction of H2O2, one thing has to be in my mind, that 1 mole of H2O2 has to get formed from its constituent elements, which must be present in their standard states. Right? Look at this reaction. 1 mole of H2O2 is getting formed from its elements which are present in their standard states. So this is the formation reaction of H2O2, whose delta H is to be calculated. Whose delta H is to be calculated. Now guys, try to understand. Call this as equation 1, call this as 2, call this as 3, call this as 4. Can I say I need to make the fourth reaction? I need to make the fourth reaction out of the given reactions. Now, how will I make this particular reaction out of the given reactions? I have to do some algorithm here. Right? Okay, so what do I do? My dear students, just if I look at all the reactions carefully, if I reverse the first reaction, let's see what do I get. Let me reverse the first reaction. When I reverse the first reaction, N2 plus 4 times H2O, it gives what? It gives your N2H4. With N2H4, you get 2 times H2O2 as well. Since you reverse this reaction, so what about its delta H now? You have to change the sign. It will be plus 800. It will be plus 800 kilojoules. Right? It will be plus 800 kilojoules. It will be plus 800 kilojoules. Right? Let me keep the second reaction as such. Second reaction I'm keeping as such. N2H4 plus O2. It gives N2 plus 2 times H2. Second reaction I kept as such. Its delta H is how much? Minus 600 kilojoules per mole. The third reaction which I have, for example, I'm multiplying this reaction by 2. When I multiply this reaction by 2, it becomes 2 times H2 plus 2 gets cancelled. So it's O2 gives 2 times H2. Since I multiplied this reaction by 2, that 2 has to be multiplied by this number as well. So delta H over here will be equal to minus 600 kilojoules. Right? Right, people? Till here, I believe everything is clear. Now, my dear students, look at these three equations carefully. Tell me, if I add these three reactions, N2H4 cancel. Right? 2 times water, 2 times water, 2 times water makes it 4 times water. That 4 times water with this 4 times water is cancelled. Right? This N2 is cancelled. So what am I left with? I'm left with something as 2 times H2 plus O2 makes it 2 times O2. It gives what? It gives 2 times H2O2. Right? I made this particular equation. How? When I added them. Since I added them, so I have to add their delta H as well. So delta H for this final reaction will be this plus this plus this. So it will be 800 plus minus 600 plus minus 600. So it is delta H will be equal to minus 400 kilojoules. Okay, when you add them, delta H will be minus 400. Now people, is this reaction and this particular reaction same? They're almost same, but only difference is stoichiometric coefficient. Right? So if I multiply this reaction with 1 by 2, when I multiply this reaction with 1 by 2, it becomes something like this. That 1 by 2 has to be multiplied with this number as well. 1 by 2 into 200 makes it what? It makes it minus 200 kilojoules per mole. So dear students, look at this particular equation carefully. Did we make Did we make the reaction whose delta H was to be calculated? Yes, we made the reaction whose delta H was to be calculated. And delta H came out to be how much? Minus 200 kilojoules per mole. I believe this is again clear to everyone. Yes? Is it clear, people? Is it clear? Is it clear? Is it clear? Now, again, one important concept. Enthalpy of neutralization. Enthalpy of neutralization. So before starting the enthalpy of neutralization, let me know once in the chats if all the things are clear till here or not. Quickly. Enthalpy of neutralization. Let me know once in the chats if all the things are clear. Guys, 1.5 hour more. That's it. 1.5 hour more. That's it. We are almost done. Yeah, say it quickly. Okay. First of all, before discussing the concept of enthalpy of neutralization, what is neutralization first of all? What is neutralization? Simple. What is neutralization? Whenever you see acid reacting with a base leading to the formation of salt and water, this particular reaction is what you call as neutralization reaction. This is what you call as neutralization reaction. Let me tell you, neutralization is always exothermic. So whenever you see acid reacting with a base, always heat will be released. It's always exothermic. It's always exothermic, right? It's always exothermic. Neutralization is always exothermic. Now, before making you understand the enthalpy of neutralization, there are a few things which I want to tell you. Do you know how do we calculate number of gram equivalents of any substance? Do you know that? Number of gram equivalents of a substance is always equal to number of moles of the substance multiplied by its n factor. Right? Okay, point number one. Number of gram equivalents of a substance is also calculated by this formula. Normality multiplied by volume of solution in liters. Just remember them directly. Remember them directly for now. Okay, this is the second formula to calculate gram equivalent. Right? Right? Now, what is the relation between milli equivalents and gram equivalents? Number of milli equivalents of the substance is always equal to number of gram equivalents of the same substance multiplied with 1000. One more result. Remember it. Next result. Normality is always equal to molarity multiplied by n factor. Just remember these results. Just remember these results. Why you need to remember these results? There's a logic behind that which you'll get in some time. First, remember these results. Number of gram equivalents of any substance is always equal to moles of it multiplied by its n factor. Right? Similarly, normality multiplied by volume in liters. Milli equivalence is gram equivalence multiplied by 1000. Normality is molarity multiplied by n factor. I believe these results you would have somehow studied before also, right? In your redox or some other chapters. Okay. Now guys, try to understand. Imagine I'm taking 1 gram equivalent of an acid. Imagine I'm taking 1 gram equivalent of a base. Imagine I'm taking 1 gram equivalent of an acid. Imagine I'm taking 1 gram equivalent of a base. Imagine 1 gram equivalent of an acid is completely neutralized by 1 gram equivalent of a base. Imagine 1 gram equivalent of an acid is completely neutralized by 1 gram equivalent of a base. the amount of heat released at that point of time is something which you call as enthalpy of neutralization. So what is enthalpy of neutralization? Since neutralization, that's always exothermic. So heat is always released, right? So heat is always released. So that's why enthalpy of neutralization value is always negative. Now, how do we define the enthalpy of neutralization? When 1 gram equivalent of an acid is completely neutralized by 1 gram equivalent of a base, at that point of time, whatever amount of energy is released, that is something which you call as enthalpy of neutralization. Okay? Now, understand very carefully. Understand very carefully. I just gave you this definition. The heat evolved when 1 equivalent of an acid is completely neutralized by 1 equivalent of a base in dilute solution. It's called as heat of neutralization or enthalpy of neutralization, right? Now guys, try to understand very carefully. For example, I'm taking HCl. Is HCl the example of strong acid? Yes. HCl aqueous. It is the example of a strong acid. I'm taking a strong base, NaOH. It's a strong base. Let them react. They will lead to the formation of salt. And with the salt, you get water as well. Okay. Imagine that I have taken 1 gram equivalent of HCl. Imagine that I have taken 1 gram equivalent of NaOH as well. Okay. Now, HCl is a strong acid. If it is a strong acid, it's a strong electrolyte. Strong electrolytes, they get completely dissociated into their ions. Strong base again strong electrolyte, which gets completely dissociated into their ions. So this HCl in its aqueous solution, can I say it would have got completely dissociated into its ions? Its ions would be H positive aqueous plus Cl negative aqueous. Similarly, NaOH, it's a strong base, again strong electrolyte, completely dissociated. So it would have got dissociated as Na positive aqueous plus OH negative aqueous. Right? This is a salt. Again completely dissociated. Na positive aqueous plus what? Plus Cl negative aqueous. And what do we have with it? With it, we have got H2O liquid as well. Try to understand very carefully. Guys. Na positive, done and dusted. Cl negative, done and dusted. What are we left with? We are left with H positive aqueous plus OH negative aqueous. What does it give? It gives 1 mole of H2O liquid. Are you understanding what is happening? I took an acid and a base. So what is happening at the end? What is the end result? End result is from acid H positive is coming, from base OH negative is coming, and at the end H positive is interacting with OH negative and leading to the formation of water. This is your end result. So first of all, you should know when acid reacts with a base, what happens actually. From acid H positive comes, from base OH negative comes. That H positive and OH negative interacts and forms water. And whenever there are interactions, whenever there is attraction, H positive, OH negative, attraction. Whenever there is attraction, energy is released. Right? So during this particular process, when H positive and OH negative interacts, heat will be released. Do you see I took 1 gram equivalent of an acid? Of a strong acid. I took 1 gram equivalent of a strong base, and I told you when 1 gram equivalent of a strong acid, when 1 gram equivalent of an acid is completely neutralized by 1 gram equivalent of a base, whatever heat released is something which you call as enthalpy of neutralization. Perfect. What happens in reality? I'll say from 1 gram equivalent of acid, we got 1 mole of H positive. From 1 gram equivalent of base, we got 1 mole of OH negative. And they interact. They are leading to the formation of water. Right? So can I define enthalpy of neutralization in one more way as well? I'll say enthalpy of neutralization is the amount of heat. Released when 1 mole H positive interacts with 1 mole OH negative and leads to the formation of 1 mole water. Right? So during this particular process, whatever heat is released, that's what I call as enthalpy of what? That's what I call as enthalpy of neutralization. So either you define enthalpy of neutralization like this, or you define enthalpy of neutralization like this. One and the same thing. And let me tell you, experimentally it has been observed, when 1 mole of H positive interacts with 1 mole of OH negative, forms 1 mole of water, heat released during this particular process is 57.2 kilojoules, right? Or in calories, you can say 13.7 kilocalories. This is the amount of heat released when 1 mole of water is formed from 1 mole of H positive and 1 mole of OH negative, right? Perfect. Since heat is released, so I'll be using the minus sign. So I can say enthalpy of neutralization in this particular case is nothing but minus 57.2 kilojoules or minus 13.7 kilocalories. Right? Right, guys? Now I need to do certain variations over here. If you look carefully, I took strong acid and strong base. I took 1 gram equivalent of strong acid, which gave 1 mole of H positive. This 1 gram equivalent of strong base, it gave 1 mole of OH negative. And 1 mole of H positive, 1 mole of OH negative interacted. And they gave us this much amount of heat. They gave us this much amount of heat. This is what I call as enthalpy of neutralization over here in this particular case. Right? Perfect. Now, guys, there are certain things which I need to tell you. Strong acid and strong base. Strong acid, strong base. When 1 gram equivalent of strong acid, is completely neutralized by 1 gram equivalent of strong base, the amount of heat released at that particular point of time is something which you call as what? Which you call as standard enthalpy of neutralization, which will be minus 57.2 kilojoules per equivalent, or you can call it as minus 13.7 kilocalories per equivalent. Correct? Correct? This was strong acid, strong base case. Now try to understand. Imagine instead of strong acid, I've got a weak acid. The base is strong. Imagine I'm taking 1 gram equivalent of this. I'm taking 1 gram equivalent of this as well. Be careful with this. I'm taking 1 gram equivalent of weak acid. And here I'm taking 1 gram equivalent of strong base. Right? Definitely there'll be salt formation and water formation. Can you tell me what will be the amount of heat released over here? What will be the amount of heat released over here? Will it be same as that of 57.2 kilojoules? Or 13.7 kilocalories? Or it will be different? Will it be same? Over here, I took 1 gram equivalent of weak acid, 1 gram equivalent of strong base, right? So will the heat release be this much? What do you think? What do you think? Will the heat release be this much? No. No. Heat released will be less than this. Why is that? Why is that? Since we have taken 1 gram equivalent of strong base. So from 1 gram equivalent of strong base, definitely you will get 1 mole of OH negative. Let's say this is your NaOH. This is your CH3COH. Perfect? From 1 gram equivalent of strong base, you will get 1 mole of OH negative. But CH3COH, it's a weak acid. Will it be completely ionized? No, it will be partially ionized. It will be partially ionized. Right? It won't get completely dissociated into its ions. So what do you get? Do you get 1 mole of H positive from here? No, you get less than 1 mole of H positive over here. Less than 1 mole of H positive. We know when 1 mole of OH negative reacts with 1 mole of H positive, heat released is 57.32. But here, no doubt, you have got 1 mole of OH negative. But here you have got less than 1 mole of H positive. So will heat release be this? No, it will be less than this. Right? It will be less than this. Or I can say it another way as well. 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 What was I expecting? How much heat should have got released. This much heat should have got released. It should have got released. But in reality, how much heat will be getting released? Less than 57.2. So if I take the difference of these two, if I, for example, this is 50.2. Let's say 50.2 joules of heat is being released. Let's say 50.2 kilojoules of heat is being released. How much should have got released? This much. If I take difference of these two, how much the value comes out to be? 7.2 kilojoules. I will say 7.2 kilojoules, this much amount of heat would be utilized to ionize this weak electrolyte. Right? So I would say enthalpy of ionization of your weak acid here in this case is 7.2 kilojoules. I hope I'm clear. How much I was expecting to get formed, to get released, 57.2. How much heat actually got released? 50.2. If I take the difference of the two, I got the value 7.2 kilojoules. That means this much amount of heat will be utilized to ionize the weak component. I hope this is clear. I hope this is clear. I'm giving you one question here. I'm giving you one question here so that it'll be absolutely clear to you. Look at this question carefully. Carefully you look at this question. From this, it'll be all clear. See guys, the enthalpy of neutralization of NaOH and NH4OH by HCl. So first of all, NaOH plus HCl. In the second case, NH4OH plus HCl. Right? What do you get? You get salt and water here. Absolutely salt water. Similarly, in the second case, what do we get? Again, we get salt water. Perfect. Now, understand carefully. This is your strong base. This is your strong acid. This is your weak base. This is your strong acid. Okay? Enthalpy of neutralization. Enthalpy of neutralization. When NaOH reacts with HCl is how much? Enthalpy of neutralization in the first case is equal to minus 13680 calories. In the second case, how much it is? In the second case, it is minus 12270 calories. Right? Can I say, in the first case, 13680 calories of heat is released? Right? In the second case, 12270 calories of heat is released. This was strong acid, strong base case. Strong acid, strong base. How much heat was released here? 13680. Now this is strong acid, weak base. How much should have been? How much should have been? How much should have been? 13680 calories of heat should have been released. But how much is getting released? 12270 calories of heat is getting released. If you take the difference of the two, 1410 calories. This much amount of heat would have got utilized to ionize the weak component. And the amount of heat which is utilized to ionize the weak component, that's what I call as enthalpy of ionization of NH4OH over here, which comes out to be 1410 calories. This is the final answer of the question. Done and dusted, right? Am I clear? Am I clear, people? This much amount of heat would have got utilized to ionize the weak component. I believe I'm clear. Am I? Am I clear, people? How to find it weak or strong? See, all your weak acids, weak bases, they are your weak electrolytes. Okay? Strong acids, strong bases, they are always your strong electrolytes. Okay, guys? Okay, one more similar sort of question. Look at this particular question. We have got dichloroacetic acid with NaOH. Heat of neutralization is this much. So this much amount of heat is released. HCl by NaOH, this much amount of heat is released. NH4OH with HCl, this much amount of heat is released. We have to calculate the heat of neutralization of dichloroacetic acid by NH4OH. Look at this question carefully again, guys. Look at this question carefully. We have got dichloroacetic acid, CHCl2COOH with NaOH. This is strong base, this is weak acid. How much heat is being released in this case? 12830 calories of heat is released in this case. In the second case, it is HCl with NaOH. HCl is your strong acid. This is your strong base. How much heat is released in this case? 13680 calories of heat is being released in this case. Third one, NH4OH. This NH4. NH4OH plus HCl. This is strong acid and this is weak base. How much heat is released in this case? 12270 calories of heat is released in this case. Now tell me one thing. Tell me one thing, guys. Strong acid, strong base. How much heat is released? This much. Make it as a reference. This is your reference. This much amount of heat is released. And strong acid, strong base interacts. Now, this is strong acid, but this is strong base, weak acid. How much heat should have been released? 13680 calories of heat should have been released. But how much is being released? 12830 calories of heat is being released. If I take the difference of 2, this is 0. 8 minus 3, 5. This will be 4, right? Correct? This will be 16 minus 8, 6. So I would say 650 calories of heat has been utilized, ionize the weak acid. So what did I get? I got the enthalpy of ionization of dichloroacetic acid. Right? How much I got it as? 650 calories. Number one. Number two. This is your reference. Strong acid, strong base. Now here, weak base, strong acid. Weak base, strong acid. How much heat should have been released? 13680 should have been released because that is the case of strong acid, strong base. But how much is getting released? 12270 is getting released. If I take the difference of the two, 0. This is 1. 1410 calories of heat. This much amount of heat will be utilized. See, this much amount of heat should have been released, but this much is getting released. If I take the difference of the two, so this much will be used to ionize the weak base. So I got the enthalpy of ionization of your weak base NH4OH as well. How much that is? 1410 calories. Correct? What am I supposed to calculate? What am I supposed to calculate? Calculate the heat of neutralization. Calculate the heat of neutralization of your CHCl2COH when it interacts with NH4OH. Now, this is your weak acid. This is your weak base. How much heat should have been released? How much heat should have been released? 13680, right? But some part of this heat would be utilized to ionize this and this. So how much is the enthalpy of ionization in this and this? It is 650 plus 1410. When you solve this, you'll get the enthalpy of neutralization of weak acid and weak base from here. I believe this is clear. I believe this is clear. I believe this is clear. Okay, is it coming out to be 850? It is 850, yeah? Sorry, this is 850. Okay? This is 850. Right? Am I clear, people? Am I clear? Am I clear to everyone? Am I clear to everyone? So what is the correct answer? What is this value coming out to be? Can you let me know in the chats? It will be coming out to be, I think, 11420 calories. So this much amount of heat will be released. So enthalpy of neutralization will be minus of this. Okay? So it has to be then option B. It has to be option B. I hope these sort of questions you can easily solve from now on. Now, one more type of question. Look at this particular question carefully. Calculate the amount of heat. Calculate the amount of heat that will be released when 300 ml of 0.2 molar HCl is mixed with 200 ml of 0.2 molar NaOH. See guys, how simple this question is. See how simple this question is. As per the question, your HCl, you are treating it with NaOH. It will lead to the formation of salt and water, right? Salt plus water. Correct? Correct? Strong acid, strong base. Now, my dear students, if I ask you, molarity of HCl is given 0.2. You know, normality is equal to molarity multiplied by n factor. N factor of HCl is 1. So normality, since this is 1, so normality of HCl is its molarity, right? So 0.2. And you know, normality multiplied by volume in liters, that gives you the number of gram equivalents. So if I ask you, initially at time t is equal to 0, how many gram equivalents of HCl do I have? So it will be 0.2, which is normality. 0.2, which is normality of HCl, multiplied by volume of HCl in liters. Volume of HCl in liters, which will be 300 divided by 1000. Correct? So 0000 cancel, it will be 0.6, so 0.06. So I have got 0.06 gram equivalents of HCl in the beginning, right? How many gram equivalents of NaOH in the beginning? What is the normality of NaOH? Molarity of NaOH is 0.2. Its N factor is 1, so its normality is 0.2 as well. So 0.2 multiplied by volume in liters, correct? So it will be 0.04 gram equivalents. So initially at time t is equal to 0, I am given with 0.06 gram equivalents of HCl, 0.04 gram equivalents of NaOH. Now tell me one thing. Over here, I'm going to use the equivalent concept. I'm not going to use a mole concept. I'll be using the equivalent concept. And equivalent concept says that the one whose gram equivalents are less, present, that is your limiting reagent. So whose gram equivalents are less? NaOH. NaOH is my limiting reagent. Okay? And equivalent concept says, whatever, since it is your limiting reagent, so it would have got completely consumed. So 0 gram equivalents of limiting reagent will be left. Now, equivalent concept says that gram equivalents of limiting reagent reacted is same as that of gram equivalents of excess reagent reacted. So I got to know 0.04 gram equivalents of NaOH have reacted with 0.04 gram equivalents of HCl. This is something which I got to know, right? These are the gram equivalents of acid and base which have reacted. Now guys, if you look carefully, enthalpy of neutralization of HCl and NaOH is given as this much. What does that mean? That means when 1 gram equivalent of acid is completely neutralized by 1 gram equivalent of base, how much heat is released? 57 kilojoules of heat is released. But as per the question, 0.04 gram equivalents of acid, right, is neutralizing 0.04 gram equivalents of base. How much heat will be getting released? 57 multiplied by 0.04. This will be kilojoules. So this much heat will be released during this process. I hope you got it. See, enthalpy of neutralization of HCl and NaOH is this much. What does that mean? That means when 1 gram equivalent of acid is completely neutralized by 1 gram equivalent of base, this much heat is released. But we already know it is only 0.04 gram equivalents neutralizing 0.04 gram equivalent, right? When 1 gram equivalents of acid and base neutralize, this much heat is released. When 0.04 gram equivalents of acid and base neutralized, so multiplied by 0.04, so this much amount of heat is getting released, right? I'll give you one more similar sort of question. And I'll write the reaction as well. H2SO4, as per the question, is interacting with NaOH. It leads to the formation of Na2SO4, and with this you get water as well, right? Strong acid, strong base. And you know enthalpy of neutralization when strong acid and strong base interacts is equal to minus 57.2 kilojoules. You know it already. Now guys, try to understand very carefully. First of all, what is the N factor of H2SO4? It is 2, right? N factor of H2SO4 is 2. If N factor of H2SO4 is 2, So multiplied molarity with 2. So it becomes 0.4. So normality of H2SO4 is 0.4. So normality multiplied by volume in liters. Normality multiplied by volume in liters. So divide with 1000 because it was an ml, right? So this value will be how much? 1.2 divided by 10, 0.12. 0.12 gram equivalence of H2SO4 we have got in the beginning. Normality multiplied by volume in liters. So 0000 cancel. It will be 1.2 divided by 10. Okay. Similarly, NaOH. How many gram equivalents of NaOH do we have? Normality. Since NaOH, its N factor is 1. If its N factor is 1, so its normality will be equal to molarity multiplied by N factor, that's 1. So that will be 0.2 only. So 0.2. Normality is 0.2. Volume is 200 ml, but make it in liters. So this 0000 cancel. 0.4 divided by 10. 0.04 gram equivalents. So as per the question, we got to know that initially we had 0.12 gram equivalents of acid and 0.04 gram equivalents of base. Equivalent concept says that the one which has got lesser equivalence, that is your limiting reagent. So which one is limiting reagent? This NaOH is the limiting reagent. And equivalent concept says that gram equivalence, if this is the limiting reagent, it would have got completely consumed. So I'll be left with 0 gram equivalence. So how many gram equivalents of limiting reagent got consumed? 0.04. And equivalent concept says that whatever gram equivalence of limiting reagent would have got consumed, same gram equivalence of excess reagent also would have got consumed. So 0.04 gram equivalence of acid would also have got consumed. So gram equivalence consumed, right? So these many gram equivalents of acid and base are getting consumed, correct? Now guys, already we know when 1 gram equivalent of strong acid is neutralized by 1 gram equivalent of strong base, how much heat is released? This much amount of heat is released. Now, in this case, 0.04 gram equivalent of acid when getting neutralized by 0.04 gram equivalents of base, how much heat will be getting released? Multiplied by 0.04. Whatever the value comes out to be, that is the amount of heat which is getting released. I believe this is clear to everyone. Yes, is it clear to everyone, people? Quick. Be very quick, be very quick. We are almost done. We are left with only few topics. There are some theoretical topics which I want to tell you now. Some theoretical topics. Some theoretical topics, people. Lattice enthalpy, I believe every one of you would be knowing. Lattice enthalpy. It is defined as the enthalpy change when 1 mole of an ionic lattice is formed from its constituent gaseous ions. Do you see in this case 1 mole of NaCl is getting formed? Absolutely, 1 mole of NaCl is getting formed from its constituent gaseous ions. These are the constituent gaseous ions. These are the constituent gaseous ions of NaCl. 1 mole of NaCl is getting formed from its constituent gaseous ions. Now, how this 1 mole of NaCl would have got formed? When they would have attracted, Na positive would have attracted with Cl negative, formed NaCl. Whenever there are attractions, energy is released, right? Energy is released. Perfect. So, when 1 mole of ionic lattice is getting formed from its constituent gaseous ions, the amount of heat released in this particular case is something which I call as lattice enthalpy. Of what? Lattice enthalpy of NaCl. And in this particular case, is the value going to be positive or negative? The value is going to be negative because energy is released in this case. Have a look. 1 mole of MgCl2 is getting formed. 1 mole of ionic lattice, 1 mole of MgCl2 is getting formed again from its constituent gaseous ions. These ions would have attracted. During attractions, energy is released. When 1 mole of ionic lattice is getting formed from its constituent gaseous ions, whatever heat is released during this particular process, that is something which I'll be calling as lattice energy of what? Of MgCl2, which will come out to be negative in this particular case because they're interacting, they're attracting, right? Yes? Perfect. Anyways, lattice energy you would have studied in chemical bonding as well. Okay, there you might have studied in different way. You would have studied it, the amount of energy needed to break 1 mole of ionic solid into its constituent gaseous signs. You can define it like that as well, no issues. Okay, so amount of energy, if I define it in this way, the amount of energy released when 1 mole of ionic lattice is formed from its constituent gaseous ions, that amount of energy released is something which I call as lattice enthalpy of that ionic solid. Okay, perfect. Perfect, guys. There is something called as heat of hydrogenation. Again, one theoretical topic. Heat of hydrogenation. Look at the definition. The heat released during the complete hydrogenation, of 1 mole of unsaturated organic compound into its saturated organic compound. For example, you have got C2H2. This is your C2H2. So I have taken 1 mole of C2H2. Okay. I'm doing its hydrogenation. It is getting converted into C2H6. Can I say I am doing the hydrogenation of 1 mole of unsaturated hydrocarbon? I am doing the hydrogenation of 1 mole of unsaturated hydrocarbon, right? The amount of energy which is released during the hydrogenation of 1 mole of unsaturated organic compound into a saturated one. This is a saturated one now. It's a saturated, right? It is saturated. It does not contain double or triple bond. The amount of heat which is released when 1 mole of unsaturated hydrocarbon, when 1 mole of unsaturated organic compound gets converted into saturated organic compound. During this particular reaction, whatever amount of heat will be released, that is something which I call as enthalpy of hydrogenation. And over here, it's going to be the enthalpy of hydrogenation of C2H2, nothing else. The amount of heat released when 1 mole of unsaturated organic compound, right, undergoes hydrogenation and gets converted into the saturated organic compound. That amount of heat released is something which I call as enthalpy of hydrogenation of that unsaturated organic compound. So basically, in your mind, there should be one thing. You have to convert unsaturated into saturated due to hydrogenation, with the help of hydrogenation. Okay? And remember, it has to be 1 mole. 1 mole of unsaturated organic compound should get converted into 1 mole of saturated organic compound. Okay? Perfect. One more term which you must be knowing, that is heat of atomization. What is heat of atomization? The amount of heat which is required. To dissociate 1 mole of a gaseous, to dissociate 1 mole substance into its gaseous atoms. If you look here, I had 1 mole of Cl2. Right? Perfect. I am breaking this Cl2 into its gaseous atoms. It gets converted into 2 Cl atoms, right? So since I have to break this bond, so heat is needed, energy is needed in this process. The amount of energy which is needed to dissociate, to break 1 mole of substance into its gaseous atoms. That is something which you'll be calling as enthalpy of atomization. And here I'll be calling it as the enthalpy of atomization of Cl2. Right? Enthalpy of atomization of Cl2. Perfect. For example, let's say I have to dissociate 1 mole of this substance into its gaseous atoms. 1 mole of this substance into its gaseous atoms. Energy is needed to dissociate 1 mole of H2 into its gaseous atoms. So whatever amount of energy is needed in this case, that is something which I'll call as enthalpy of atomization of H2. Right? Isn't it simple? Isn't it simple, people? Perfect. So in short, what is enthalpy of atomization? It is the amount of heat which is needed to dissociate 1 mole of substance into its gaseous atoms. Right? Since heat is needed, so the process is endothermic. Since heat is needed, required, so the process endothermic. Again, one simple thing. Again, one simple thing. Now, look at this conversion diagram. Look at this conversion diagram carefully. See, first of all, for example, this ice, so solid, right? Liquid and vapor, this is gas. Conversion of solid into liquid at its melting point. Conversion of solid into liquid. Conversion of solid into liquid at its melting point. The process overall is called as fusion. The process is called as fusion. Conversion of liquid into its gas at its boiling point. Right? The process is called as vaporization. The process is called as vaporization. Conversion of solid directly into its gas, at its sublimation temperature. At its sublimation temperature. The process is called as sublimation. These are the three things which I believe everybody of you would be knowing already. Right? Solid into liquid at this melting point is called as fusion. Liquid into gas at its boiling point, vaporization. Solid into gas directly at its sublimation temperature. The overall process is called as sublimation. Now here I'm going to define enthalpy of fusion, enthalpy of vaporization, enthalpy of sublimation. Now tell me how you guys are going to define it. How you guys are going to define enthalpy of fusion? How do you define enthalpy of fusion? When 1 mole of solid gets converted into 1 mole of liquid at its melting point. When you convert solid into liquid, heat is required, right? Heat is required. So whatever amount of heat is required to convert 1 mole of solid into 1 mole of liquid at its melting point, that is something which you call as enthalpy of fusion, right? The amount of heat which is required to convert 1 mole of liquid into 1 mole of gas at its boiling point, that amount of heat required is called as enthalpy of vaporization. The amount of heat which is required to convert 1 mole of solid directly into 1 mole of gas at its sublimation temperature, that is called as enthalpy of sublimation. Simple, done and dusted. Right? Am I being clear? Am I clear to everyone? Am I clear to everyone? You can see it over here. The amount of heat required to convert 1 mole of solid into liquid at its melting point is called as 1 mole of solid into 1 mole of liquid at its melting point is called as enthalpy of fusion. Right? The amount of heat which is required to convert 1 mole of liquid into 1 mole of vapors, 1 mole of gas at its boiling point. That heat required is called as enthalpy of what? Enthalpy of vaporization. Same is for enthalpy of sublimation. Same is for enthalpy of sublimation. Okay? Then guys, there is something called as bond dissociation energy. There is something called as bond dissociation energy, right? These are few last topics. I don't think I'll take more than half an hour to complete this chapter. So half an hour more, that's it. Half an hour more, that's it. Okay? The amount of energy. Two questions will come from this. Okay, two questions. The amount of energy required to dissociate. Be careful with the terminologies. The amount of energy required to dissociate 1 mole of a gaseous bond, 1 mole of a gaseous bond into separate gaseous atoms. Into separate gaseous atoms. What does that mean? For example, let's say I have got 1 mole of H2 gas. I have got, for example, 1 mole of H2 gas, right? See, H2 means it will be like this. Okay. So can I say, see, in one molecule of H2, there is one bond present. There is one bond present. Can I say, in 1 mole of H2, there will be 1 mole of these gaseous bonds present? In 1 mole of H2, in 1 mole of H2, there will be 1 mole of these gaseous bonds present. In order to break the bond, energy is required. The amount of energy required to break 1 mole of gaseous bonds so that it gets converted into its gaseous atoms. So that it gets converted into gaseous atoms. The energy required in this particular case is something which I call as bond dissociation energy. So this is the bond dissociation energy of H2. Bond dissociation energy of H2, right? For example, I've got 1 mole of Cl2. Can I say 1 mole of Cl2 contains 1 mole of these gaseous bonds? These gaseous bonds? In order to break the bond, energy is required. The energy required to break 1 mole of gaseous bond into its atoms, into its gaseous atoms, right? The amount of energy needed in this particular case is something which you call as bond dissociation energy of Cl2. Bond dissociation energy of Cl2, right? Bond dissociation energy of Cl2. Now guys, if you look at it very carefully, I need to basically tell you one important thing. For example, I have got 1 mole of CH4 gas. I have got 1 mole of CH4 gas. Okay, CH4. Tell me one thing. In 1 mole of CH4, how many moles of CH bonds are there? Can I say in 1 mole of CH4, there are 4 moles of CH bonds? Right? In 1 mole of CH4, there are 4 moles of CH bonds. Correct? Now, for example, in 1 mole of CH4, we have got 1 mole of this bond, 1 mole this bond, 1 mole this bond, 1 mole this bond. For example, you are breaking 1 mole of this bond. What do you get? You get CH3. You get CH3 plus H. Right? Perfect. The amount of energy needed in this particular case, let me call that as bond dissociation energy 1. Let's say that's X kilojoules. Let's say that's X kilojoules. Now, what do we have? CH3. CH3 gas, right? In CH3 gas, in 1 mole of CH3 gas, how many CH bonds are there? There are 3 moles of CH bonds. Let's say out of those 3 moles of CH bonds, I'm breaking again 1 more mole of CH bond. It gets converted into what? It gets converted into CH2 gas plus H. The energy needed in this process is something which I call as bond dissociation energy 2, which is, for example, X2 kilojoules, right? Now, I'm left with 1 mole of CH2 gas. In 1 mole of CH2 gas, there are 2 moles of CH bonds. Out of those 2 moles of CH bonds, imagine I need to break 1 mole of CH bond. Imagine I need to break 1 mole of CH bond. What do I get? CH plus H. CH plus H. Amount of energy needed in this case at bond dissociation energy 3, that is X3. That is X3. Now what do I have? CH gas. CH gas. 1 mole of CH gas, what does it have? It contains 1 mole of CH. In order to break that 1 mole of CH, so that it gets converted into C gas plus H gas. Let's say bond dissociation energy in this particular case is X4 kilojoules. Is X4 kilojoules, right? Is X4 kilojoules. Now, my dear students, look at all these reactions. How many reactions do we have? How many reactions do we have? How many reactions do we have? Quick. How many reactions do we have? 4, right? Bond dissociation energy of the first one is X1, second one, X2, third one, X3, fourth one, X4. Which bond was I breaking? I was breaking CH bond, right? If I take the average of these, X1 plus X2 plus X3 plus X4 divided by 4, this is something which I'll be calling as bond energy of C. So there's a difference between bond dissociation energy. These were bond dissociation energies of CH. This is something which you call as bond energy of CH. Bond energy is basically the average of all these bond dissociation energies of CH. Did you get all these things? Did you get it, people? Did you get it? Let me know in the chats quickly. Did you get it? I'm giving you one more case. Let me give you one more case so that you can understand it carefully. For example, I've got 1 mole of NH3 gas. 1 mole of NH3 gas contains 3 moles of NH bonds. Out of those 3 moles of NH bonds, imagine I'm breaking 1 mole of NH bond. So I get NH2 gas plus H, right? Energy needed in this particular process is bond dissociation energy 1, which is x1 kilojoules, right? Right, people? Look at this particular case. Now we have got 1 mole of NH2 gas. 1 mole of NH2 gas contains 2 moles of NH bonds. Out of those 2 moles of NH bonds, I'm breaking 1. I get 1 NH gas plus H gas, right? Energy needed for this particular process is something which I call as x2 kilojoules, right? Now, NH gas to convert into N gas plus H gas. N gas plus H gas. Energy needed in this particular case is your X3. What is this X1, X2, X3? What is this X1, X2, X3? These are the respective bond dissociation energies of NH. If I ask you, what will be the bond energy of NH? I was breaking this bond only. Bond energy of NH. It will be X1 plus X2 plus X3 divided by 3. Average. Am I clear, guys? Am I clear with all these things? Am I clear with all these things? Now, guys, now at the end, one thing from which surely question comes in your exam. One thing from which question surely comes in your exam. What is that? Calculation of enthalpy of reaction from bond energy data. There's a result which needs to be derived, but I won't be deriving that. I'll give you the result directly and I'll show you how to apply that result from which you'll be getting the questions. Understand? Understand. My dear students, remember, enthalpy of the reaction is always equal to your bond energy of reactants minus bond energy of products. This is the result. How do we write it? How do we use it? That is important. That is important. My dear students, for example, I'm writing the reaction. Reaction is like this. N2 gas plus P times H2 gas. It gives 2 times NH3 gas. It gives 2 times NH3 gas. Look at it very carefully. Look at it very carefully. N2, the structure is like this. N triple bond N. 3 times H2. The structure is like this. H2. NH3. NH3. This is N, H, H, and H. Perfect. N, H, H, H. Now, my dear students, if I write enthalpy of the reaction is equal to bond energy of reactants. I'll start with the reactant. What about its stoichiometric coefficient? 1. 1. And then energy need to break N triple bond N. Perfect. This one is done. Now go towards your H2. Stoichiometric coefficient is 3. And this bond we have to break. Energy need to break HH bond. So this is your bond energy of reactants minus bond energy of products. So first I'll write 2. How many NH bonds I need to break? 3, right? So 3 times energy needed to break NH bond. Perfect. In the question, this data, and this data, it will be given. When you put it here, you'll be getting the enthalpy of this particular reaction. Right? Let me give you one more example. For example, you have got C2H2 plus 2 times H2 gives C2H6. This is the reaction. For example, this is the reaction. Imagine I need to calculate enthalpy of this reaction. I need to calculate, for example, enthalpy of this reaction from bond energy data. How I'll be doing it? Bond energy of reactants minus bond energy of products. First of all, know the structure, C2H2. C2H2 is like this. This is your C2H2. Now 2 times H2. H2 is like this. C2H6. This is your C2H6. This is your C2H6, right? This is your C2H6. Now, enthalpy of the above reaction is equal to bond energy of reactants. Stoichiometric coefficient here is 1, right? So nothing to do with it. So how many types of bonds do we have here? 2 types of bonds. One type is CH, then CC. So how many CH bonds? 2 CH bonds. 2 CH bonds you have to break, and you have to break one C triple bond C bond. One this bond you have to break. And apart from this, stoichiometric coefficient here is 2. And there is one bond. So energy need to break this HH bond. So this is your bond energy of reactants minus. Talk about your products. In your products, stoichiometric coefficient here is 1. Okay. Now, how many types of bonds do we have? 2 types of bonds. One is C single bond. One is C single bond H. Right? How many CH bonds do we have? 6. So 6 CH bonds we have to break. And how many CC bond you have to break? 1 CC bond you have to break. Right? 1 CC bond you have to break. In the question, all these things will be given to us. When you put it here in the question, you'll be getting the enthalpy of the reaction. Guys, are you getting all these things? Are you getting all these things? Are all these things clear to you? Can you let me know once in the chats quickly? If all the things are absolutely clear to you, then only I can show you certain questions. Look at this question. Calculate the enthalpy of formation of HCl. Calculate the enthalpy of formation of HCl. So first of all, you have to write the formation reaction of HCl, and this is the formation reaction of HCl. 1 mole of HCl is getting formed from its elements which are present in their standard states. This is the formation reaction of HCl, right? Now, calculate the enthalpy of formation of HCl, right? So since 1 mole of HCl is getting formed, so enthalpy of reaction here, what it will be called as, you can call it as enthalpy of formation of HCl as well, because 1 mole of HCl is getting formed. And I've told you already, when 1 mole of substance gets formed from its elements present in their standard states, enthalpy of reaction is called as enthalpy of formation. Right? So, first of all, this is half of H2. This is your H2. This is half of Cl2. Right? And this 1 times HCl. So, enthalpy of the reaction is equal to bond energy of reactants. So, half of this is HH plus half of this is Cl-Cl bond minus product. Stoichiometric coefficient 1. So this is HCl. Correct? You're done. This is half of bond energy of HH. The bond energy of gaseous HH is given as 104. So this is 104 plus half of Cl2 is 58. It is 58 minus HCl. HCl is 103. Right? Solve it. Get the enthalpy of the reaction in kilocalories per mole. Right? It's a matter of calculation now, nothing else. It is a matter of calculation now, nothing else. Nothing else. Can you solve this question? Calculate the heat of hydrogenation of ethene. First of all, take ethene. This is your ethene. You are doing its hydrogenation. Right? What you'll be getting? You'll be getting ethane. So first of all, 1 mole of substance, 1 mole of unsaturated organic compound undergoes hydrogenation and gets converted into saturated compound. Enthalpy of this particular reaction is something which you call as enthalpy of hydrogenation. Of what? Of ethene. Correct? So basically, we have to calculate enthalpy of this reaction. Now, look at this particular reactant. Enthalpy of reaction is equal. Look at this particular reactant. In this one, how many different types of bonds we have? 2 types of bonds. CH and CC. How many CH bonds? 4 CH bonds. Right? How many CC bonds? 1 CC bond. Perfect. H2. Its stoichiometric coefficient is 1. Right? So H we need to break here. Now comes to the products. On the product side, what do we have? On the product side, we have got 2 types of bonds, right? Out of which 6 are your CH and 1 is your CC. 1 is your CC. Now I think all the parameters are given. This is given to me, 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 this is given to me. Put the values and get the answer. That's it. Right? Right, people? I hope I'm clear with all these things. Let's do one more question. The dissociation energy of CH4. The dissociation energy of CH4 is 360. Right? And dissociation energy of ethane is 620. Calculate the bond energy of CC. So dissociation energy of CH4 is how much? 360 kilocalories per mole. Dissociation energy of C2H6 ethane is how much? 620 kilocalories per mole, right? So over here, how many bonds we have to break? 4 CH bonds. So in order to break 4 CH bonds, how much energy is needed? 360 kilocalories. So in order to break 1 CH bond, 360 divided by 4 is 90 kilocalories. So this much heat is needed in order to break 1 CH bond, right? Over here, C2H6. In case of C2H6, how many types of bonds do we have? C2H6. So we have got 6 CH bonds we need to break, and there is 1 CC bond we need to break. Perfect. CH bond is 90. 6 multiplied by 90 plus CC bond is equal to 620. So energy need to break CC bond here will be 620 minus 9 6 are 54. So this is 540. So this will be how much? 80 kilocalories per mole, right? That's something which I was supposed to calculate. So this is the bond energy of your CC. I hope I'm clear. I hope I'm clear. I hope I'm clear. Right? Perfect, guys. And one last question. With that, we'll end the session. With that, your thermochemistry part is clear. And ask me, guys, 2 questions. Sure shot you'll get from this session. Sure shot 2 questions. Should I give you this as the homework? Should I give you this question as the homework? Will you do it on your own?